Hello and welcome back to Calculus 2. Today's section is on sequences. It's covered over the span of two sections in the textbook. And we are going to do the same thing we always do, define the concept and then try examples and then be done, right? Some of these problems will be very short. Some will require proofs within the problem to be done. Very rudimentary and basic, but still needed. So let's start with the definition. Sequence is an ordered list of numbers. Next sentence, also definition. So sequence is an ordered list of numbers. That's pretty much what it is. And next definition says that your counter, hold on, I have. Now, counter actually, we don't need this one. I'll explain when I work out some examples. What do you need as a prerequisite? What you need as a prerequisite is limits at infinity and L'Hopital's rule. There you go. So those are the two things that we need. We need to be able to take the limits as x goes to infinity, and we also need to be able to use L'Hopital's rule when we are presented with a little bit more interesting. You know what I mean. All right. So now let's take a look. The first sequence that I could relate to, let's go and have, so we want a sequence, right? Example of the sequence would be n equals 1, 2, 3, 4, 5, and so on. So this is a sequence. When I say ordered list of numbers, that sequence is ordered through the set of natural numbers. So now it's the other definition. Ordering is done in respect to so ordering, meaning which number goes first, which number goes second in the sequence. So ordering is done in respect to set of natural numbers n. Set of natural numbers n. And n is the element of the set of all natural numbers. It's the double bar, capital N, for the notation. Now let's see another example over here. Say, oops, no need to be dramatic. So an is equal to 1, 4, 9, 16, 25, 36, 49, And you already recognize this pattern, right? What is this?
It's the square numbers.
Square numbers, very good. So now, what we are doing is we're going to assign x0, x1, x2, x3, and as long as there are no gaps in these, so now what happens? Well, we have the one-to-one correspondence between each of the numbers in the beginning of our sequence, and then we have x0 matching the first one, x1 matching the next one, and so and so. So whatever number you have, you will be stretching these x's as we go. Now, easier way to write this clearly would be to just write, well, this is n squared. That's what it is, a sequence. Try it. When you're so for number one, well, this starts at number one. So when you start with number one, you have 1 squared, and it's going to give you 1. Then you go to the next one. So if this is 1, that will be 2. So 2 squared over there is something is off.
Did you label x1 at 1 and x2 at 4?
Oh yeah, it's shift. Yeah, this is. It's not supposed to start with 0. All right. So the small numbers are the values that you are plugging in. No problem. So when I say an, this n over here is the set of all natural numbers, and generally that goes from negative infinity to positive infinity. However, the an, or in our case, we generally use, we could use negative numbers, but we don't. So generally we use that n is the set of counting numbers. So n. So here. So n is the set of counting. There we go, much better. Counting numbers. So now, if I have a sequence written as an is equal to x squared minus square root of x, whatever. You can, oh, not x, n's, sorry, n's. Main variable for chapter 8 is n. The book will frequently use k, I believe. So whatever you have, it's fine. So this n is just a number, right? You will get here on a first pass, you will get there on a second pass because there's a pass here and a pass there, right? So that's 2. Now this one is 3, but apparently they can charge a little bit more, right? So, just trying to see which way. I gave you the formula, and I gave you the formula, and I gave you the way the numbers that you plug in. Those are index numbers. That's the input, and that is the set of counting numbers. We could start at 0, but we can also start at 1. Generally, you use whatever is the most convenient to put the formula together. I could have started an with 0, in which case I would have x0, and then you will have 0 squared will give you 0, and so on. So they have one-to-one correspondence. Ordering has to happen over that set n. Ordering has to happen over the set n. So you see that there is order 1, 2, 3, 4, 5, 6. Yeah, I understand that over here was 1, 4, 9, 16. You can have fractions, you can have a whole bunch of stuff happen, right? You have to figure out the way, what is that core, right? And what are all the mathematical operations that would go back so that you can use 1, 2, 3, 4, 5, 6 to order all of these numbers. So now, if we go to the next line down there, the last one that I posed, your A1. So now what is the sequence? Sequence, guys, this is a list of numbers, so it's just going to be commas, and you just plug all of the numbers in. So we start at 1. So you have n squared, that will be 1 squared minus square root of 1. 2 squared minus the square root of 2. 3 squared minus the square root of 3. 4 squared minus the square root of 4. 3 dots, and you end the set. This will go on forever. Now when you compute, right, when you compute this, you will get 0, 4 minus square root of 2, 9 minus square root of 3, 16 minus 2 is 14, dot, 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 going on forever, right? Next one would be 5, 5 squared, 25, 25 minus root 5, that would be next one. So they don't have to look, quotes, nice, right? They can be whatever they need to be. However, you have to be able to somehow trace it all the way back to the original formula for which you used x1, x2, x3, x4, x5, x6, and so on, as an input, right? As an input. So, to recap all of this from the beginning, sequence is an ordered list of numbers. All of you in this classroom, you are the list of students, and I go name by name, right? Now, I can order you by increasing social security number, increasing passport number if you're all citizens, or increasing height, or increasing body weight, or increasing whatever, right? We can find characteristic that, you know, will describe you. So you will all have different social security numbers, and if I'm to pick all of the social security numbers, I will be able to put them in an increasing order, and that will determine the order in which I would, right? But we can also do the last name, the first name, and, you know, we can do ordering in many different ways. Now, for sequences, we're lucky we don't have to worry about any of this other ordering other than you order through a set of natural numbers. So your sequence will either be generated by n equals 0 and then 1, 2, 3, 4, or n equals 1 and then 2, 3, 4, and so on. So sequence is an ordered list of numbers. Observe that it's a list, so you have just commas in between. And we are going to order that through n. Let's take a look at another example. Bn equals to 3n plus 1. Right? So, what is the sequence? Start with n equals to 0. So let's go with the 0. 0 is not a part of counting numbers, but we can still use it. So, because you don't count 0 students and then 1, 2, 3, 4, 5. You just go 1, 2, 3, 4, 5. All right, so use the formula and get the first 5 terms for the sequence. No call. I think I skipped one, right?
Yeah.
I skipped 13.
Yeah.
All you need to do to write out this sequence is to keep plugging in discrete variables. In our case, right, discrete variable, the counting variable, and that will be n, which is either 0, 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, and so on. So with or without 0, depending on the case, and problem will tell you start at 0 or start at 1, if you are to expand any of these things. Now, the question is, how do we go back? Right? Can we somehow deduce the formula if the numbers are given to us? Oh, there's so many of these cheesy ones. Okay, let's try. So 26 would be straightforward, and then I will show you some interesting stuff. So we have 2, 5, 8, 11. It's too dramatic. Can you come up with a formula? You have this. You have the first 4 numbers. This is going to go forever. I should have put in 3 dots right there. 1, 2, 3. There we go. So that indicates it's going to go forever. So there will be a value at 17, and there will be a value at 133, and so on. Now, can you devise a formula? Or 1. I'm going to leave that up to you. Some of you might start at 0, some might start at 1. I don't. Here we can do both in this case. So let me see what you come up with. So your job is to come up with a formula. We used to have the formula and then write the sequence like that. Now you get the sequence. Can you get the formula by looking at the pattern? And as I said, make sure mathematically correct. I don't care whether you start at 0 or you start at 1. Very few applications are sensitive to that in this. So there are a few strategies that you would employ to figure this out. Number one is, look at the spacing between the numbers. Do you see it's always plus 3? Right? Plus 3, plus 3, plus 3, plus 3, plus 3. So now, somehow I need to capture that. I need to start at 2, right? And then get to 5, 8. So, the way I do these problems is I do this in my head, but I'll have to write it here. So I subtract whatever is going to make me go to 0. So if I do this, I keep in store that I will have plus 2 later on because I just did minus 2 out of nowhere. Eventually we'll have to add the 2 so it balances everything out. Now this becomes the new sequence, and this one is 0, 3, minus 2, 6, minus 2, 9. Do you see? So you see now the pattern, right? If you look at the values, these are what? Multiples of 3, very good. If you are to divide this by 3, you would end up at 0, 1, 2, 3. So all of the decomposition that we are doing now is going to be, we subtract 2 out of nowhere. We'll have to fix that later with the plus 2. And then we divide it by 3 out of nowhere to get us all the way back. Right, so this warrants that we are supposed to have times 3 later. So if you multiply out of nowhere, divide out of nowhere, or do anything out of nowhere, you have to put this counter here, and then you will remember to place that into your final goal. So now, once you are here, making this formula is easy, because this over here is your n, and you see over here what you need to do to it. You need to triple it and add 2. So n needs to be tripled because that is it, right? You're plugging n for this. This is times 3. So times 3. So n times 3 is 3n, and then at the end plus 2. And now it would be cool to test this, right? Remember we started at 0. So now I want to, so this is what we came up with, right? an is equal to 3n plus 2. So let's now check. Green, check. So how do we check this? Well, you take a random value, right, from a domain, and you plug in the formula and see if it is the same as was posed in the original problem. So if I go and I say, all right, I want to work on when n is equal to 2. For n is equal to 2, I am calculating a2. a2 is going to be 3 times 2 plus 2, and that is 6 plus 2, and that is 8, and I do have an 8 there. Now, is this location n equals 2? Well, hell yes, because it's 0, 1, 2, 3, right? So we were able to confirm. We were able to confirm that our method, I mean, this is not a proof, right? This is something that says it works. Let's try one more of these, and this time it should be a little bit spicier because you already, let's go with spicy. You got this, right? So again, write the formula. I will give you the sequence. 64, 32, 16, 8, 4, going on forever. Let's see what you get. Remember the method, right? You are trying to get to either 0 or 1 on the first term. And once you have that 0 or 1, pretty much reading all the other steps that you wrote down the line will give you the formula. All right. Did anyone figure out the formula? So this is the spiciest they offer in the section. This is problem 30.
You just like keep going until you get 0, 1, 2, 3, 4.
Uh-huh. So what's the formula?
Well, I got not quite there yet, but like I was working for you. I got the first two.
You got the first two. If you have the first two, you have them all.
What? Really?
Yeah.
I got 0, 1, 3 has 7 fourths and 15 eighths. I like to subtract at 64 to get 0.
But that gives you negative 32.
And then I divide it by negative 32. And then I was going to just keep going. I don't know if that would be cool.
Just keep dividing.
Well, then I was going to multiply by whatever.
All right.
Then probably
Matt. Yes.
You want the formula?
Yes.
128 over 2 to the n.
128 over 2 to the n. You like spicy food?
It's just too spicy.
All right, so the report is that this is the answer, right? Now, the way I'm going to do this is I'm going to divide over here by 64, right? If I divide everywhere by 64, I'm getting 1 on the first one. So, since I divided by 64, I know it will be times 64 later. Now, when I divide by 64, what I get is 1, and then 1/2, and then 1/4, and then 1/8, and then 1/16, and then goes ... forever. And that's it. Because over here, I have everything I want. You see, this is in the denominator, right? I can write the first one as 1/1 if it's going to help, right? Write as 1/1. And now you see that your numerator for the formula is always 1 divided by, and now denominator. The way it grows is either 2 to the n or 2n. Those are the two options that you guys have, right? So now if it's 2n, well, 2n is just even numbers, so it can't be 2n, because 2n would give you for n equals to 1, it will give you 2, and then for n equals to 3, it will give you 6, right? 4 gives you 8, so it's 2, 4, 6, 8, 10, 12, right? So all even numbers if you use 2n. Now 2 to the n, well, that might work, right? So 2 to the n, and now you start placing your values to check. So the first value is 0, so 1/2 to the 0 is 1 divided by 1 is equal to 1. It checks on the first. Now you say, all right, so they had tested for 3. No, which one was this? 0, right? That was test for 0. All right, so if you test for, let's say, n equals to 3, what happens with an n equals to 3? Oh, I forgot to say over here, times 64. There we go. So if n is equal to 3, we have 64 divided by 2, 4, 8, 16. Huh. What happened? 2. Oh yeah. Yeah, but it still doesn't address my. Ah, yeah, started at 0, so my fourth number is 8. So that will be a number that we don't have here, right? No. Yes. So 64, this would be for 2. N equals to 2. So if you apply n equals to 2, it's okay, good, it works. Alright, so 64 over 2 to the n. I mean, you know what I mean. Good.
It's through the end.
Why did I? Yeah.
Does it change if you have 0?
Yeah. Alternating sequences. So we'll have alternating series as well. That's all the way, I believe, in the last section of chapter 8, 8.6. Alternating sequences are going to be ordered list of numbers where you have some kind of a behavior repeating. So the quickest example for alternating series would be -1, 1, -1, 1, -1, 1, -1, 1, and then I'll put 3 dots because that is supposed to continue forever. So alternating sequence or alternating series later on, right, they are going to have terms that swap between positive and negative. So that's what we have for our alternating sequences. And to portray this one, we're just going to call it -1 to the n. Because if you can see, when n is equal to 1, that's where we start, n equals to 1. So when you have n equals to 1, then you have -1 raised to the +1 exponent. Well, that's just going to be -1 because it's negative times itself. I mean -1. Then you go n equals to 2. When you plug in 2 over here, it becomes a square. That kills a negative, so that's why the next one is positive here. And it goes like that. Flip-flop, right? Now your textbook is asking you to come up with a formula for alternating sequences with 5s and -5s. So, do the same thing. For -5, oh, I have to send it, okay. Let's go 5, -5. There we go. So see if you can, you have 4 5s over there in a row. They're all uncommon. Yes?
In the previous problem, to get 1 over 2 to the end, you just like to basically guess that. Not guess, but
It wasn't a guess.
no, but
We see
We
that.
like-
I'll show you the pattern. You have to know the
you just had to derive it from the pattern. There's no actual math to do to get that formula. You have to look at it.
Oh, you're looking for, yeah.
Okay.
You are looking for a procedure that can be mechanically done. Sometimes it divides, sometimes it multiplies, sometimes it adds, subtracts. So it depends on what the problem is. Should have put the comma there. I should have closed. So what do we have?
5 times -1 to the end.
Beautiful. You kick out 5 and you just do that. You cannot put -5 to the end, because -5 to the end, as you start changing ends, you would run into 5 squared. That will give you 25. You don't have 25 on the list, right? Or n cubed. That will be 125. N to the 4, 625. None of those numbers are on the list. So your job is to factor out 5 first. When you factor out 5, you're left with this, and this is that. So you just plug it there times 5. Now let's check. When n is equal to 0, it kills this term. The first one is 5. When n is equal to 1, that survives as a negative. 5 times negative 1 is negative 5, which is this one, right? So they all work just fine if you have it this way. Good. So that will be on the alternating. And now these alternating series sequences, they creep up into the others. We'll eventually learn in chapter 9 a very cool way to write trig, and they will sneak up. So they will be there. Okay, so that's alternating sequences. Let's see what else, if anything, we can do. The graphs. So you are no longer dealing with linear mathematics. You are dealing now with the discrete mathematics. And discrete mathematics doesn't have curves and lines as the graph. Now it has these distinct points. And each of the data points is above its own x index, right? X sub 1 or 2 or whatever input. So if I go and say that an is equal to, and then you give some kind of a data here. But see, the trick is that it has to be ordered. So the pattern must exist, and you can come up with a formula, right? So let's go with formula 2n plus 1. Now, 2n plus 1, starting at n equals 0, right, is going to be 1. And then when n is 1, it's going to be 3. And you quickly see that these are just odd numbers. Now, it's very, very smart and useful to remember the formulas for quick reference, right? So that you know. So which ones are you quickly remembering? Remembering n, 2n, n squared, 2 to the n. Like these are the ones that we deal with most of the time, right there. Yes.
I have a question about the last one. I was just confused. This one you would start at down right, so it's 1.
No, you start at 0.
But then this one starts at 1. There's a negative 1, so it's 0.
You can put plus minus on the top. We'll deal with that. So let's graph this. Input values 0, 1, 2, 3, 4, 5, 6, 7, 8. And an goes on the y-axis because that's what we're graphing. Versus you don't have x-axis anymore. Now this is n. Right? It's the n-axis. All right, so we have 0 and 1. And then we have 1 and 3. And then 2 and 5. Okay, so that's that, that's that. So there they are. That's the graph. Now, if you want to make this continuous, you strike a line through this, and you change that n into x, and you get your 2x plus 1, which is the linear straight line, right? Well, now this is also the form mx plus b, mx plus b. So it's in the same boat, right? In terms of what we're doing, that it would be, well, you graph point by point, but if you were to graph the linear line, right? The linear line would go like that. Now, these are just the certain values because you are not allowed to plug into sequences any value you want, right? So you have to be careful about that. But that's the graph. There's nothing more to it. It's just a whole bunch of dots, right? Above 1, above 2, above 3, above 4, right? Because that's your input, 1, 2, 3, 4, 5, 6. Now, came to my attention over here that this one over here is wrong. It was supposed to contain either +1 or a -1 on that n on top in the exponent. So I'll just add -2.
Could you put a negative on the outside of -1? Also give you the same thing?
Wait, why is it -2? It needs to go -1. So now, when n is equal to 0, or if you start n equals to 1, right, n equals to 0, n equals to 1, that's a 0. I will have to put that negative out in this case. Let's see.
So if you put a negative on the outside of -1,
Yeah.
it would work.
Yeah, we'll have to. There's a negative in front. Right here.
Without the -1.
And without the -1 now. So we have n to be 0. So -1 to the n would be, to the 0, right, would be 1. And then 1 times the negative is -1. Okay, next round, what do we have? We factor out 5, and then when you factor out 5, but now the signs are opposite, so it matches. Okay, good. Why are these computers shutting off every 15 seconds?
So should we start off with 0 or 1?
Whatever.
In that case, if you start off here. In this case, you start with 0. Yeah.
So then all of them would have been right if we started at 1.
Yeah, it will.
Yes.
So we can start at 0 or 1.
You can start at 0 or at 1, or at 2, or at 3. You can start at 17.
Should we just label what we start at so that?
Yeah, I did over there, starting at 1. But now we need to say start at 0, right?
We gave it starting at 0, so we had to use.
Yeah.
So
That's
if you tell us what it starts on?
Then you know, yeah.
Okay.
Otherwise, it's whatever. Yeah, this exam is a little bit tougher to debate. But, yeah, we'll manage. All right. What else for sequences series? For sequences only. So it's ordered list of numbers. Ordering is done through the... Yeah. There you go. All right, so now we are going to have a whole bunch of stuff, and this is very important. By the way, guys, if you are a computer science major, it's your stuff, right? Because you see the counter, right? You see that n. It's the backbone of any loop or statement like that in your computer science programming class, right? So for computers, it's 1 or it's 0, right? So over here, either divergence or convergence, we'll see that. But what's important is that for each tick in time, you don't have anything in between these. You just have the next dot, wait 3 seconds, next dot, wait 3 seconds, next. You can compute the, right? Compute that stuff. Now, in blood, this is the first one you are memorizing. Test for convergence. Of sequences. There's only one test, and so this is a theorem. Theorems is what you use to compute stuff, right? To calculate, to solve problems. So theorem is simple. If the limit as n goes to infinity of an equals L, then sequence converges. Otherwise, it diverges. So now you get to see if the sequence that you are looking at, is it finite or infinite? Meaning, is it some kind of, well, let's put it down. Let's do the problem. It will be clear immediately. So say you have an defined as n squared and have bn defined as 1 over n squared. So these are the two sequences given to you, and you want to test for convergence. Convergence means as it goes to infinity, it kind of settles at a value. And I'll give an example from physics, but let's first finish this. So now the test for the sequence, and the only test we know so far, right, is this one. So limit goes to infinity of your function is now n squared and now you compute this. You see that it's infinity. Now on the other side, limit n goes to infinity, 1 over n squared as n goes to infinity, and as n goes to infinity, right, the value of this particular expression remains as 1 over a large number, which is 0. So this one tends to 0. By the way, can we use L'Hopital's rule? Yes or no? No. Because L'Hopital's rule is for infinity divided by infinity. You have 1 divided by infinity. It doesn't work. So we have to do it the different way. Alright, so now, if you take a look at the graphs for the first quadrant, right, we have n squared. So I'm just going to, there we go. Graph the other one, and you will see quite opposite. Ooh, that was terrible. That was terrible. Don't look at it. I'm going to shut everything off. So this is what it looks like when it's not compressed, when it's continuous, like that. Now, if I could, I would just go and assign buttons to the shirt right there. So what I can do is, if you 1 over n squared, it's going to look like this. Now, observe that your values, right, fall towards the n-axis. It's not gonna, right? But the important thing about the test is, and what does it mean, converge, diverge? Converge in this case simply means it settles at the value. And I think one of my exams has it somewhere, depending on the version, where you are supposed to take a derivative and figure out how fast have to take a derivative, figure out how fast the disease is spreading, right? Well, in the problem that is posed, it says that there are 25,000 people living in the town, I believe. 25,000. Can more than 25,000 get sick? No, right? Because 25,000 is all you have, and once that gets, if everyone manages to get sick, we never had everyone get sick and die, because you look around, we're here, right? For centuries upon centuries, we've been chased by everything else, right? And later on, the hygiene and all of the other stuff that was bad in the cities created the plagues that went through, right? And wiped out maybe even 2/3 of the population of Earth, but still, not everyone died, because as you can see, we are here, right, talking. So, in that case, the problem is bounded at 25,000, and that would be your limit. And you would say converges to 25,000, because it is right the answer of the limit. Now, if you look at one to the left for n squared, this grows without bounds. Does not get close and snuggle right in like this one. There are many of these, and then obviously they will give the rise to even, crazier concepts later on. First time you see this is in differential equations course, but you can also see it in physics. So if you write y equals e to the negative at times cosine of bt, right? This is motion in 2D, right? And it's a wave that diminishes in time. So you say this is with dampening, meaning it's going to die. So that means it's going to die out. This is a cosine, so you will start over here, and it bounces down and does this. And it dies out as the x-axis goes. You see the limit of this here is 0. Right, limit is 0 because I don't care what's happening here for the short period of time. Remember, I'm taking the limit all the way to infinity. So I'm wondering what's happening here. Right, all the way to infinity. You can see it starts strong, it starts losing its. If you put the spring to dangle off of the ceiling, right, put some weight, it's going to go like this, and then eventually it's going to stop at its equilibrium. So that motion is captured with this. Now, that's a continuous signal. Can I have a discrete one? Sure. We already have this point, and then maybe this point, and this point, and this point. I don't know how many points are necessary for you to measure. But as you can see, each one of these has its unique divisions and so on. All right, so let's see. Test an equals to n plus 5 over n raised to the n. Go. No, I mean go. So we are testing for convergence or divergence. We want to see if this settles around the value or goes to infinity. So, does it settle or grow without the bounds? What is your verdict? Anyone? It's finite? If it's finite, okay, so what it converges to? Nope. Nope. It's not 1 and it's not 5.
Does this involve L'Hopital?
There's no,
I think
no need.
That's how I can get behind.
What? No, it's not infinity. I agree that this converges. All right.
It's not 5?
No. Matt, what's the answer?
E to the 5.
E to the 5.
Same thing.
No.
It has a 5 in it.
Oh, really?
Closer than 1.
Okay. The pain.
How is it even 5?
We are supposed to look at the limit n goes to infinity. Guys, this limit is extremely important. It's going to show up 15,000 times throughout this chapter. 15,000 times throughout this chapter, so strap in, right? What I'm going to do is I'm going to break this into 2 separate fractions. This becomes now 1 plus 5 over n to the n, which is e to the 5. Yes, you are supposed to know that this is definition for e. I don't care whether you know that from Calc 1 or you know it from Calc 2. Now that you are in sequences, this is common knowledge. You know, I ask you what's your name, you say, my name is whatever. Then you go and say, oh yeah, that's E. And I did cover this here. Did I? Let me see. There it is. Look at that. 6.8. Right. And I show you which ways you can get the exponent. This is number 2. The 1, 2, 3. It's the middle one. Right? 1 plus 5 over n. That's the middle one. And you get e to the 5, e to the a. Whatever a is, that's the exponent. Or you can have the exponent b on top over there. So b goes, right, no matter where the exponent is.
Why is it E?
Well, we can do the L'Hopital rule to show that it's e, but this is the definition for e. And you can use logarithmic method to take this limit. So those of you that are still struggling with this, well, that's it. You ran out of your lives, and now it's here to stay. So why? Because limit n goes to infinity of 1 plus 5 over n to the n can be set to equal to, say, a value y. Then we ln both sides, so we get ln y is equal to the limit n goes to infinity, and over here we are going to have ln of 1 plus 5 over n. And now instead of placing this n on top, we'll put the n in front. So that's the one that escapes in front when I add the logs. So now I have ln y is equal to limit n goes to infinity. And now over here, what do I have? I have infinity times 0. So, since I have infinity times 0, I write ln 1 plus 5 over n. Everything divided by 1 over n. Okay. The next order of business is to, now that you have 0 over 0, right? This is 0 over 0. if you plug in infinity, you get 0 over 0. So you can use L'Hopital's rule. L'Hopital's rule, so we have not the limit, ln of y is equal to, and now we put this L apostrophe h, which says that we actually did the chain rule.
1 over 0 is 0, and 1 over 0 is on the top.
I'm plugging in infinity. And goes to infinity. So 1 over infinity is 0. Derivatives. Negative 1 over n squared, that's the denominator. In the numerator, I have 1 plus 5 over n times its derivative on top. No, it's just 1 plus 5 over 9. Wait, it's already used up. So put that there, and then its derivative on top, so that's going to be negative. No, because you are taking the derivative of the whole thing over here. Think about it. If it's 2 out of infinitely many points, right? So it's good to go. It's the derivative.
Yeah, that's what I said.
Did you?
Oh, I brought down negative 2. So.
And then minus copy the no, that's it. That's it. All right, so now when you simplify this, you should come up with number 5. And then e both sides, and you get y equals e to the 5. But now let's do this. So times n squared. Let's go with the negative n squared. I will kill the negative as well. So ln y so L apostrophe there we go. All right, so now this is so times n squared times n squared. So clears that one. So these guys cancel. So negative cancels. I'm just trying to pick the colors that won't distract. So now you see that everything in the denominator canceled, and you are left only with the numerator, which is the limit 5 over 9 You're supposed to say n, not 9. I can't write it anymore. 5 over, so this is gone, this is gone, this is gone, so it's 5 over 1 plus 5 over n. There we go. And we still have the limit in front, which is going to n goes to infinity now. So now this part over here will go to 0. There we go. and you see that the entire numerator is 5 over 1, which everything becomes 5. So now we have ln y is 5, and then you e both sides to get y alone, and you get that y is e to the 5. So that's why. And as I said, guys, you have to go back to lecture 6, right? And I mean, you know, it's a choice. You can do that limit long way every time, or you can memorize the formulas for E. Now, you were supposed to know these formulas from Calc 1. And then we did the refresher, as you can see, in 6.8. Well, now we're going to need this pretty much every day. Yes?
So if it's, say with the b equals, or e to the n equals ln, the limit is, essentially, say you combine the bottom two. You have like a over n to the bn, would just be e to the ab.
Yes.
Got it.
Yes. So if you combine,
Yeah.
if you have a b over here, it will be b over there as well, so you will have e to the ab. So you can have them all at once, yes. Good question. So this is the test, guys. Test for convergence of sequences. Now, we will say, right after this calculation, that problem converges to e to the 5. Because that's what you got in your answer, e to the 5. So it can converge to 0, it can converge to 3, it can converge to any number. Decimals are allowed. You are not allowed to use decimals in the input, but the output, right, it can be a decimal number. E to the 5 is a decimal number, so you have to deal with that. Good. Our computer is shut off again. Nice. Also, all that it's left is just few definitions, and we can do, if you want, we can do more limits. Okay. Where are the definitions? I can't find them.
Bounded monotopic sequences.
Yes.
Squeeze down again. Oh god.
Yes?
That was like the worst thing in California. That was the one question on the test, like, everybody got wrong. It's not that difficult, like, in retrospect, but it was just that, you know,
Oh.
I need to go back.
Okay, so we have few of these definitions. Terminology for sequences. Definitions, this is page 608. And then you have 5,000 of these 7, but 5,000. So what do we have? We have the definitions. So number 1, AN is increasing if AN plus 1 is bigger than AN. For all n. Well, it better be increasing if the next term is bigger than the previous term. So if whatever is constantly growing, getting larger, you are going to have that the latest point you're computing is at the higher level, right, higher elevation than the old point. And now you have the term for non-decreasing. So AN is non-decreasing if AN plus 1 larger equal to AN. Number 3, where AN is decreasing if, and now you have to swap the condition up there, so AN plus 1 less than AN. So the new, right? New, and then in this case smaller than the old. And then we have the non-increasing. So it's non-decreasing when AN is, so if AN plus 1, then AN. Right. And now we have monotonic and bounded. So the function is monotonic if the either non-increasing or non-decreasing. Okay, so we'll say AN is monotonic. So AN is monotonic if it is either this is monotonic, okay, if it is either non-increasing or non-decreasing. Okay, and 7, AN is bounded. if there is number m such that absolute value an is less than. Good. So those are some rules, and now let's take a look at some problems. Yes.
What is monotonic? For example?
So okay, so if you're thinking about, so monotonic is when it's either non-decreasing or non-increasing. It's just a name to put them together. These guys, to put them together. So what is the difference? What is the difference between increasing? So in order to understand all of these, let's go and get them all examples so it makes sense. So first we start with increasing, right? So for increasing, observe that you are strictly to bring in higher values. So if something is increasing, the simplest one for us to show off would be n, which is 1, 2, 3, 4, 5, going on, right? So that's number one. When you have that an is increasing for all n, and then we have the new minus the old. Now the next one is number 2. Now the number 2 says clearly non-decreasing. Well, if it's non-decreasing, then it must be, what's opposite? Increasing. Good. But look what is the difference between them. This one had every new term to be strictly bigger. This one can kind of, yeah, it's a repeated, right? So if we wait a little bit longer, we'll be away from that situation. So the non-decreasing one allows for repeats in your data, in your sequence. So I can say this one is n equals 1, 2, 3, 4, 4.1, 4.3, and then 5, and that's it. All right, good. So now, would you agree that this is increasing? Right? You would. But you have to be very careful because it doesn't fit our. And this is why I said, the common sense, you have to memorize things. So both of these are increasing, right? But look at this one. It has 1, 2, 3. Hold on. Supposed to have repeated value, and then 4, and then 4. What were the decimals I had?
1.
And then 4.3 and 4.5, right? All right, good. Now, both of these are increasing, but the second one, look, 3 and 3 over here. And if you have 3 and 3, that's, so this is just non-decreasing. That's what its name is. Now we have the other next two would be the same way. So we need a decreasing function. Decreasing function would be cool to have, let's say, 1, 1/2, 1/4, 1 to the 8. That's too much. There we go. And then what we have? Same thing here. except you allow for at least one repeat. We don't need this here. And then numbers 5 and 6. So now monotonic means if it's either non-increasing or non-decreasing. So non-increasing and non-decreasing. So this one and this one. Monotonic means constantly, like something is monotone, like it's the same all the time, doesn't change, right? So if the function starts at the downward thing, it will go downward forever, right? If it's x squared and it goes up, it goes forever, right? So monotone, it doesn't really change. What's its kryptonite? Sine, it always changes. The sine oscillates all over the place. Good. I think it's time to learn a little bit more about limits, or to refresh our mind from before. I told you that the two main ideas for you to take limits, because pretty much every limit, not pretty much, every limit goes to infinity. Instead of cranking those long calculations, sometimes you can only look at the limit using the growth rate of functions. So this is a very important part. So we'll say growth rate, and I will immediately draw a jar over here of some kind, right? There you go, growth rate. For exponential growth rate, it's not that you have to, pack stuff into the bottle so you can fit more. For exponential model, you need to find another bottle ASAP, and pretty much as soon as you find it, it will be full. And then, but you will have it at 0.8, right? You could double it again and double it again. So growth rates, exponential growth rates are very fast, and then below them we have polynomials and square roots and ln's, right? So we have few of these categories. Get rid of the bottle over here, and put the growth rate from, I'm using the same notation that the book uses. So the slowest growth rate is going to be attributed to the ln. So we have ln so okay, so ln to the q u. And I like the curly brackets. Okay, fine. So we have ln. Okay, if this not, whatever. I'll explain later. All right, so let's go. So first one is ln. The second one is the polynomial. Then the next one is polynomial times the ln. And then we have n to the p plus r, which grows slower than b to the n, which is slower than n factorial, and that all is slower than the boss, right? And to the end. All right. So here we go. Logs are the slowest. And then with logs in the same pile you have the square roots. Then you have your n squared, n cubed, n to the 10th or whatever. then if you multiply these two together, you get this one, which is faster than any one of these. And then this is polynomial times another polynomial. You know that exponents add, but this is polynomial times polynomial. So look, you have these creatures individually, then you multiply them to create something faster. Now what I want to do is I want to take the slow ln and put another polynomial in there. When I multiply polynomials, their front coefficient powers add. So now, all four of these, they are ruled by the two polynomials which multiply each other. Now, that is going to be slower than any exponential growth. So there's the exponential growth there. And now, that is going to be in terms slower than n factorial. We haven't dealt with this yet, but we need it. I will have a talk on factorial, obviously. It's needed. And then, finally, the boss, n to the n. All right? Now, what do you do to show and prove it to yourselves that this makes sense? Well, all you need to do is to compute chart of values. And as soon as you compute chart of values, it will all make sense. So let's say this is n squared, 2 to the n, n factorial, n factorial, and the last one over here to be n to the n, which is the boss. Now pick 1, 2, 3, 4, 5, and 6, and then populate the entire chart using these values. Who picked these numbers? We can skip the factorial column and go immediately for the one at the end, because you know what that one is. I'm going to write the numbers for the factorial, but we'll have a full lecture on those. N to the n. I have to use abacus for this because these numbers are going to get huge. Obviously 1 to the 1 is 1 and 2 squared is 4. And then we need 3 to the 3. Like 3 to the 3, that's 27. And then to the 4th. Yeah, 256. And now we have a 5. So 5 raised to the 5. How much?
I wrote this 5 and 45 is 3,125.
Yes, yes.
I just thought that this was interesting. Like, this is the same thing that I saw when I was learning big O notation in computer science. Yeah,
this is the base for it. Yeah.
Yeah, the complexity of algorithms.
Yes.
It's the same thing.
It's 1.5 and then times 5.
Oh, right.
Yeah. 3,125, yeah. 3 factorial. 6. And then 4 factorial is 24.
Yes.
And then it's
all right, so 127.20. Okay. Guys, observe the growth rates from your vanilla growth rate, 1, 2, 3, 4, 5, right? It goes by 1, into these. Now observe that eventually each one of these overtakes, and they are actually for the last calculations, for the last few calculations that we do, the ones that are supposed to be better, which are at the end, are better. I mean, faster growing. Note that factorial lost to both of these, right, on the third spot. But immediately on the fourth spot, it made it up. And then over here, it took off. And then just like, went flying. Right? Yes?
How do you define how large B is? Because you could just set it to like 5 billion to the end.
Yes.
And then it would be bigger.
For a very long time, and then eventually the other one will win. Yes.
So
As soon as you get to 5 billion more.
Because, see, the trouble is that we as humans have that limitation to count because we don't have the luxury of time or patience to count all the way to infinity. Computers have the same issue as well. Computers are going to deal with large numbers and give you the answer that might have, 5, 6, 10 pages of digits, right? But eventually computers stop. I'm not sure at which point, but I don't know, 10 to 60 something. The computers are no longer able to portray one type of a number. I think odd numbers or whatever. So computer eventually is no longer able to read certain numbers or to store certain numbers because information is lost due to the way we design computers and everything else that goes into that mix. Now the thing over here, we say limit of, as n goes to infinity, of fast over slow is going to be infinity, and the limit of slow over fast is going to be 0. Now, when do you get numbers? When you take two functions that have the same or similar growth rate, and then you are really, comparing those together. But we will not need that in this course. So, if you have a faster, so if this is factorial over polynomial, and polynomial could be to the millionth degree, it doesn't matter, the top is going to win. That's it. Sequences, right? Done.
I can ask what sequences at this point.